Okay, so yeah, I have to admit, in my previous lecture, so attendance was really low. I hope you, by now, I hope you have seen the video lecture. But in spite of that, so I really feel like I have to somehow summarize my previous lecture, especially on the Jordan form and Jordan matrices. So every square matrix is similar to some Jordan form. So you know the difference between the Jordan form and Jordan blocks and Jordan form. So this is a Jordan block. Jordan block is a K by K matrix, which is almost diagonal matrix, whose diagonal entries are all lambda zeros, and just one entry on the above. So they are all ones, and all the other guys, they are zero. So this is a Jordan block of size K, and Jordan form is a almost diagonal square matrix whose diagonal blocks are each of these Jordan blocks. Jordan form is every square matrix is similar to some Jordan form, and therefore the Jordan form is a complete matrix invariant. So that means you can actually compute. So there is a very concrete algorithm that computes Jordan form of any square matrix, and if those two Jordan forms, if they agree, then I am 100% sure that those two matrices are similar. So in that sense, I am calling the Jordan form is a complete matrix invariant. Okay. And also, there's very important thing to point out that, so this guy, so there is only one eigenvalue, one and only eigenvalue of this matrix, which is lambda zero, and is algebraic multiplicity is K, right? So if you can trust me, then just try to compute the characteristic polynomial of this matrix. So, and this guy has algebraic multiplicity K and the geometric multiplicity equals to 1, right? So therefore, what do you think is the eigenvalue of this matrix? Well, so all these diagonals, they are all lambda zeros. Therefore, it has only one single eigenvalue, which is again lambda zero. And what do you think is algebraic multiplicity? Since this matrix is so here I am assuming the size of each of these matrices as each of these Jordan blocks are K1, K2, KL. Therefore, this is a square matrix of size this times that, right? This is square matrix of this size. And I am pretty sure that the eigenvalue of this guy, the only eigenvalue of this matrix is lambda zero, and whose algebraic multiplicity is precisely the size of this matrix, right? And what do you think is this geometric multiplicity? Well, the geometric multiplicity is L because, well, each of these Jordan blocks contribute precisely 1 to the geometric multiplicity of that eigenvalue, right? And here we have L such Jordan blocks. Therefore, its geometric multiplicity must be L, right? So, okay. And also, there's one important idea. That is, if two matrices are similar, then they share almost all important properties, such as eigenvalues and their algebraic and geometric multiplicities. And if the size of A is small, so precisely, if size of A is less than or equals to 3, then a Jordan form of matrix A is very easy to determine. Just all you have to do is just compute the algebraic and geometric multiplicities of eigenvalues of A. That's it. But if size of A is greater than or equals to 4, then you might encounter some trouble. So just like this. Suppose that A is an eigenvalue lambda 0, and suppose that this eigenvalue has algebraic multiplicity 4 and geometric multiplicity 2. Then the possible Jordan form of this matrix is either this or that. Why? Because for both of these cases, the algebraic multiplicities of lambdas are 4, right? 4 and 4 because the size equals to 4, and it has 2 blocks. Therefore, its geometric multiplicity is 2 and 2, right? So there is actually 2 possible options. So also you don't need to worry about the order of these Jordan blocks. Okay, so how do you determine the Jordan form of the matrix? So that is going to be the very important question for today's lecture. So I will try to explain that. There are 3 important facts that will be used. The first one is, if A and B are similar, then the nullity of A equals to nullity of B, which is very obvious, right? So, okay, so I'm going to take the fact number 1 for granted. And fact number 2, for any square matrix A, so A to the k, the null space of A to the k's power is always contained in the null space of A to the k plus 1 first power. So why is that? Because if x belongs to the null space of this guy, then by definition, so A to the k times x equals to 0. Now, what I want to do is I want to multiply the both sides of this to the left by the matrix A. Then A to the k plus first times x equals to the 0 vector, right? So that means x belongs to the null space of this space. So therefore, we prove this inclusion. Oh, by the way, please allow me to use this slide because, well, I just realized that we have only 5 lectures left. So this is week 13, this 13th week, and we have 1 additional lecture besides of today's lecture. And so yeah, we have 5 more lectures, but we have still long way to go till the end of this semester. So I need to deal with the positive definite matrices and singular value decompositions. So sorry about that. So this is the reason that instead of trying to write down everything on my iPad, but I prepared my small own slide. So for today's lecture only, okay, please allow me to do my lecture using this. Thank you. Okay, and fact number 3. So fact number 3 is somehow ambiguous. So it tries to prove some very weird identity. So okay, so what does it say? I have a Jordan block. So this is not a Jordan form, but this is a single Jordan block, and whose size is m. So this is an m by m matrix, and with eigenvalue lambda 0. Then this factor number 3 is trying to say something about the nullity or dimension of the null space of this guy, this matrix, right? The null space, the dimension of the null space of this matrix is 1 if k equals to 0. And after that, as you increase the power of k by 1, then the dimension of the null space increases also by 1, right? And eventually, the null space, the dimension of the null space of this guy equals to 0, equals to m if k is greater than or equals to m. So that means, so nullity of this matrix stabilizes if your power is getting sufficiently large. So in other words, the nullity stabilizes for large enough k. Okay. All right. Why? Okay, hold on. So J minus lambda 0 times I, this is again an m by m matrix. And the nullity of this m by m matrix equals to m that means after this point, this matrix is going to be the zero matrix, right? There's only one n by n matrix whose nullity equals to n, which is the zero matrix, right? Okay, so let me try to prove this. Well, this is my Jordan block. So please, let me say this is an n by n matrix, n by n matrix with single Jordan block. I have all bunch of lambda zeros and all ones here. And yeah, so this is a single Jordan block. And j minus lambda 0 times I is going to be this, right? And what do you think is the rank of this matrix? Well, I have n minus 1 non-zero rows here, and I have 1 0 rows at the bottom, on the bottom. Therefore, the rank is n minus 1, and the nullity is 1. So which is dimension of null space of this guy is 1. Okay. Okay, so this is good. Now, I want to raise the power of this matrix. So this guy is squared. This is very simple computation. So if you square this matrix, then what you're going to get is the bunch of zeros here, and another zeros over there, and another diagonal, which is purely consisting of ones, and all the other guys equals to 0. Okay, so this is your j minus lambda 0 times I squared. So if you cannot trust me, then why don't you just try this computation by yourself? Then you can easily be convinced. Okay, now what is the rank of this matrix? I have non-zero rows from here to there, and I have 2 0 rows, right? So rank of this is n minus 2. Therefore, the null space is nullity is 2. Yeah, yeah. I know this is getting somehow tedious, but just take just one additional power. Let me take. So what happens if I take the third power of this matrix? Then 0 here, another 0 there, and another zeros, and I have ones over there, and all the other guys 0, right? And in this case, rank is n minus 3, and the nullity is 3. So can you read the pattern over from here? So as you increase power one by one, this bunch one is moving one step to this corner, and the rank increases by 1, and nullity increases by 1. Okay. Okay. But the nullity cannot increase forever, right? At this point, if you raise the power of this matrix by power of n minus 1, then eventually you're going to have just one single one over here, and all the other guys equals to 0, right? And in this case, rank is 1 and nullity is n minus 1. And if your power is greater than equals to m, then you will just end up with 0 matrix. Everything equals to 0. So nullity is m, and after this point, no matter how large power you take here, then nullity is still going to be m. So this is actually the proof of the theorem. Okay. Okay. All right. Okay, let us keep this in mind. And now we are ready to determine the Jordan form of any matrix. So this is my idea. Suppose that let us suppose that A has only one distinct eigenvalue, which is lambda 0. So if your matrix A has more than one distinct eigenvalues, but you can actually determine the Jordan form of that matrix without too much trouble, because if you can determine the Jordan form of any single eigenvalue, then you can actually apply the same trick to another eigenvalues, and you know how to find the Jordan form of the matrix. So because of that reason, so I will only focus on a matrix that has only one single distinct eigenvalue. So I want to determine the Jordan form of the matrix A. The idea is this: we compute the nullity of this matrix and find the algebraic and geometric multiplicities of A, and we list all possible Jordan forms of A. And based on the nullity of these matrices, we can guess the correct Jordan form of the matrix. Okay. Yeah, I don't think the explanation is very crystal clear. So I will try to work on some concrete example. So let me try to determine the Jordan form of the matrix. Well, so first, so you are supposed to compute the characteristic polynomial of the matrix. So which is very somehow routine computation. So I did it for myself. So which is lambda minus 1 to the 4th. So it has only one eigenvalue, which is 1, right? And what is this algebraic multiplicity? 4, right? Okay, good. Now, I will need to find the geometric multiplicities of this eigenvalue. So to do that, so I computed a minus 1 times I, which is this, and using some elementary row operations, I just ended up with this ugly looking matrix. And how many linearly independent rows can you find from here? Only 2, yeah. Even though I have 3 non-zero rows, but this guy is clearly linearly dependent to the third one. So the rank of this guy is 2, therefore the nullity is 2. So the nullity is 2 means the dimension of the null space of this guy is 2. That means this eigenspace of this guy should be 2, right? Eigenspace means the null space of this one. Okay. So this implies, so this is 2-dimensional space because nullity is 2. So the geometric multiplicity of this eigenvalue must be 2, right? So this is algebraic multiplicity 4 and geometric multiplicity 2. So what are the possible Jordan form of this matrix? In this case, I think these 2 Jordan forms are the possible Jordan form of matrix A. Why? Because each they are both eigenvalue 1s, right? It has eigenvalue 1s, and its algebraic multiplicities is 4 and 4, and their geometric multiplicities are both 2, right? Because it consists of 2 Jordan blocks. So we need to determine which one is the Jordan form of the matrix A. Okay, how do we find it? So how do you know which one is the Jordan form of A? All right, so this is my trick, this is my idea. So what I want to do is, what I did was, I tried to compute A minus I squared. So I just take the power of the square root, the second power of this matrix. Well, this is some tedious computation, so I did it by myself. And I just ended up with this matrix. And how many linearly independent vectors can you see here? There's only one linearly independent row vector, which is 1. So its rank is 1 and nullity is 3. And I just raised just one additional power of this. So A minus I to the third power. Oh, and I just got 0 matrix. So rank is 0 and nullity is 4. Okay. So based on this computation, I am quite sure that the Jordan form of this matrix is this guy, not this one. Why? Why? Because suppose that the Jordan form of this guy equals to this. Okay. Then, sorry. If this guy were the Jordan form of the matrix, then okay, J minus I is going to be what? 0, 0, 1, and 0, 0, 1, right? Which is still the nullity of 2. But if I raise the power of this matrix, then what I'm going to get is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, so whose nullity is 4. Okay, but this computation clearly says that a minus I square has nullity not 4 but 3. So therefore, nullity of square does not match to the nullity of this guy. Right? So because of this reason, this guy cannot be the Jordan form of A. But so if this guy were the Jordan form of A, then everything just matches clearly. So J minus I is, in this case, 0, 0, 0, 1, 1, and 0. And raising to the second power, I will get 0, 0, 0, and 0, 0, and 1, and still 0 here, right? And raising to the one last power, I will get 0, 0, 0, 0, 0, 0, and 0, right? And let me compute the nullity of each of these matrices. Nullity is 2, 3, and 4, which is precisely the case of this, right? Because the nullity of each of these matrices matches to the nullity of these matrices from A minus 1, A minus 1 to the square, A minus 1 to the third. Therefore, because of this reason, this guy must be the Jordan form of the matrix A. This is how you determine the Jordan form of any given square matrix. Okay? Okay. All right. No. All right. So I have one. So I just figured one additional exercise. This is 5 by 5 example. So, well, so I computed the characteristic polynomial, and which is lambda plus 1 to the 5th. So that means it has only one distinct eigenvalue, which is -1, and whose algebraic multiplicity is 5. And I want you to determine the Jordan form of the matrix. Okay. So this will be very nice thing and educational exercise. All right. Okay. So this is a huge digression. And now let us go back to our original track. So last time, we tried to compute the matrix exponential of this matrix. So do you remember this? So it has two distinct eigenvalues, plus imaginary unit I and minus of imaginary unit I. And it turned out its matrix exponential is just nothing but some rotation. Okay, cosine t minus sine t, and cosine t. All right, but I want to say this is not just coincidence. So this is very kind of typical behavior of very special kinds of matrix. I suppose that I have some square matrix A, which is n by n, a real matrix. So that means whose entries are all real numbers. And suppose that this matrix is satisfying this condition. If you take a transpose of matrix A, then it's going to be the minus of itself. So such matrices are called a skew symmetric matrix. So skew symmetric means this is not exactly symmetric, but almost symmetric matrix. Okay. So and if A is a skew symmetric matrix, then whose is matrix exponential ETA is an orthogonal matrix for all real numbers T. Hey, so do you remember the orthogonal matrix? So what was the orthogonal matrix? So orthogonal matrix was defining property of the orthogonal matrix is a square matrix whose inverse is its own transpose, right? Okay, so to prove this, I will need to show that the transpose of this guy is inverse of itself. So because of that reason, so I try to take a transpose of this matrix exponential. And this is our definition of the matrix exponentials. So, and I take a transpose here, but taking transpose here, so is just a transpose of this matrix part. So a to the k, everything taken transpose. But so same matrix A has been multiplied k times. So this integer k and the transposition, they can be interchanged. So this is at raised to the power of k, right? And I wanna understand this as the matrix exponential of ET A transpose, right? So I am taking the matrix exponential of not A, but A transpose, right? Okay, so this guy equals to that. So ETA transpose is ETA transpose. But we are assuming that A is a skew-symmetric matrix, so A transpose can be replaced by minus A. So, and e to the minus TA is the inverse of ETA. Why? So if you do not quite get it, then just try to remember this relation from my previous lecture. Yeah, so EST times ETA is the summation. So therefore, and also the matrix exponential of the zero matrix is going to be identity, right? Therefore, this one must be the inverse of this matrix. Okay. Okay. Also, very interesting property here. If A is skew-symmetric, then the matrix exponential of the skew-symmetric matrix has determinant 1, always. Okay, so why? Why is that? Yeah, okay. So because of the previous proposition, we now know that ETA is always an orthogonal matrix. So, and the possible determinant of any orthogonal matrix should be either +1 or -1. Why? Because every orthogonal matrix times its own transpose is going to be the identity, right? So its determinant should be either +1 or -1, right? Okay, good. And yeah, so this must be somehow a very new argument to you, but I say that the function determinant is a continuous function. So why? Well, we can understand the determinant as a function from the space of all n by n matrices to the real numbers, right? But the space of all n by n matrices also can be understood as Euclidean space of dimension n squared, right? Because the matrix of n by n matrix has the n squared many independent entries, right? So this is actually the same as the space of this Euclidean space of dimension n squared, and determinant is actually a polynomial defined on this space, right? Yeah. So must be continuous. Okay. All right. So what I want to do is I am composing this function with the matrix exponential ETA, and whose possible outcomes is outcomes are plus or minus 1, right? And so this is a continuous function. So and the point is the domain of this function, codomain of this function is two discrete points. And if your function is continuous, it cannot allow any jump discontinuity, right? So in order to be continuous here, then your function value must be either constantly plus 1 or constantly minus 1, right? Because continuous function can never allow any jump discontinuities. But I'm pretty sure the function value of this guy can never be minus 1, because if you plug in t equals to 0, then it's going to be identity, so which is plus 1. So therefore, determinant of ETA has to be always constantly plus 1 for all t. Okay. In particular, if you plug in t equals to 1, then determinant of the matrix exponential of A should be 1, right? Okay. So, well, going back to this example, this is a skew symmetric matrix, right? This is skew symmetric, very easy to see here, and whose determinant is 1, right? And yeah, and this is an and this is an orthogonal matrix. The last corollary here is if A is skew symmetric, then any solution of U prime is A times U. Yeah, this represents a system of differential equations of order 1, right? Do you remember this? And this system of differential equation always satisfying the condition. So the magnitude of vector ut is always the same as the magnitude of at t equals to 0. Always the same as the initial condition. So in other words, so if A is not skew symmetric, then your solution vector ut will have magnitude will either go to positive infinity or either tending to 0 or somewhere else. But if your matrix A is skew symmetric, then your magnitude, so your vector ut may somehow rotate about the origin, but the length of your vector ut always remains the same. So in other words, this is a neutrally stable system, right? So if not neutrally stable, so do you remember that if your system is stable, then your solution vector ut will eventually tend to 0, or if not non-stable and tends to 0, then it will go to positive infinity. But the magnitude just carries over, implies that this one has to be the neutrally stable. Okay, so proof of this is very easy. We know that the solution of this system is the ETA matrix exponential, ETA times the initial condition vector U0. And I try to compute the magnitude square of the solution vector. So which is this guy transpose multiplied by itself. And the U0 transpose and ETA transpose and ETA, but these two guys, they are inverses to each other, so they just cancel. So it's going to be U0 everything squared. Okay. All right. So we are turning to the next chapter, next section, the complex matrices. So if you are following my lecture, well, then you now somehow understand the dealing with complex matrix is somehow mandatory. Why? Because even though we are working on the world of the real matrices, but the eigenvalue could be some complex numbers. Therefore, in that case, you should be able to understand somehow dealing with the matrix with complex entries. So but I say there's nothing to worry about the complex matrix. So every computation, every algorithm they just carry over. So you can actually do the LU factorization on the complex matrices, and you can also try to compute the determinant of the complex matrix. The algorithms are just exactly the same. But there's only one difference. What is that? That is the notion of the length. So why? Okay. So I just prepared a tiny little example. So let us consider this vector. This is a complex matrix or complex vectors. So this is two-dimensional complex vector, 1 and I. And I want to compute the length of this vector. And how do you compute the length of vector? So to compute the length square of any vector, then usually you are supposed to take a transpose of the original vector and multiply it by itself. Then the resulting number is going to be the length squared, right? So I did exactly the same thing here. So 1i times 1i, then 1 times 1, which is 1 squared plus I squared. But I squared is -1, therefore 0. So the length of this guy turns out to be 0. But I don't like this. Why? Because so I want to have in my book, the length of any vector should be 0 if and only if the vector is the 0 vector. But if I use this inner product, so I would say this, if I use this concept of length, just we did in the real vectors, then I might have some non-zero vectors whose length equals to 0. So in order to avoid this, I want my length of vector to be something more like that. So suppose that this is my n-dimensional complex vector consisting of alpha 1 to alpha n. So and here alpha 1 to alpha n, they are all complex numbers. And I require my length to be precisely my length squared to be the alpha 1 squared, alpha 2 squared, alpha n squared. So here so what is the magnitude of complex number? Do you know how to compute the magnitude of any single complex number? Yeah, you know how to do this. You just multiply the complex number with its own complex conjugate, then it's going to be the magnitude square of that complex number, right? So therefore you take a magnitude square of this first entry and magnitude square of second entry, and you add them all together. Then I want this guy, this number, this real number. I want this real number as a length square of my complex vector. So how do I develop such a nice notion of vector, a notion of length in the world of the complex matrices? And we define a new notion of complex inner product defined like this. Well, I just figured some wild notation of v to the h, but this h means you take a transpose of this matrix and you are taking the complex conjugate to each of these entries. Oh, sorry. And I want to define this guy to be my new inner product for the complex vectors. Okay. Then, if you take an inner product of vector v with itself, then the answer is precisely the magnitude of every component squared. Then we now have this desired definition of the complex length, the length of the complex vector. So this is going to be my new inner product. But if you're paying attention to my lecture, then this is not a completely different inner product. Actually, this notion of inner product actually contains, generalize our notion of inner product in real vectors, right? But this is not a new definition, but this is a generalization of the inner product in the world of the real vectors. Okay, so from now on, for complex vectors, this is our inner product, and this is our length of the length of the complex vector. And in this case, the length of any complex vector equals to 0 if and only if V is a 0 vector. Okay, great. So this is the only difference. There is only one difference. This is the only difference between the real vector matrices and the complex matrices. Okay, and I feel like I have to give you the precise definition of this tiny little h over here. So this is definition. Let A be n by n complex matrix, then A to the H is an n by n matrix, so M and M, they will switch it, such as AH is defined to be a complex conjugate and taken transpose. Easy, right? Definition is not horribly complicated. This is what I call a, from now on, we're going to call this guy as conjugate transpose or the Hermitian of matrix A. So this is Hermitian. So, and complex inner product, V, W is defined to be the V Hermitian times W, right? Oh, by the way, so there is one very important properties regarding the complex inner product. You know, for real inner product, real vector V inner product with W is same as W inner product with V, right? They were the same thing. But that is not true, and that is not true anymore for the complex inner product. So if you compare V inner product with W and W inner product with V, then you can realize they're exactly complex conjugate to each other. Because this H contains the complex conjugate. So this is very crucial difference. And next, now suppose that A is an square matrix, n by n square matrix, that is such that whose Hermitian matrix is itself. So if there is in other words, matrix A is an invariant under complex conjugate. Then we say A is an Hermitian matrix. I really don't like this naming because the Hermitian of A and Hermitian matrix, they are somehow very confusing to each other. Well, okay, but that is done by choice. So, well, so A, so in this case, if A is a Hermitian matrix, then this is invariant under complex conjugate. So, well, this is you should understand this guy as some sort of a complex version of a symmetric matrix, right? For real matrix, we had the notion of the symmetric matrix, which was invariant under transposition. In the world of complex matrix, alternatively, we have notion of the Hermitian matrix, which is invariant under complex conjugate. So I just prepared, I just prepared a tiny toy example of the Hermitian matrix, and this is Hermitian matrix. Just try to take a conjugate and transpose, but it doesn't change anything. Well, there's a very important thing that you will need to know that is every Hermitian matrix has real diagonal entries, right? If there is some imaginary numbers involved in the diagonals, then it cannot be a Hermitian matrix. Okay, and these guys, they are complex conjugate to each other. Okay. Okay, all right. Now, I want to talk about the eigenvalues and eigenvector of a Hermitian matrix. Hermitian matrix is a complex matrix, but in the world of complex matrices, you can still have the notion of the determinant. You can compute the determinant exactly the same way as we did in the real matrices. So you have the characteristic polynomial, and you have the exactly same notion of the null spaces. So you have eigenvectors and eigenvalues for complex matrices. Okay. The proposition number 1. I have a n by n square Hermitian matrix. Then, for any complex vector, complex n by 1 column vector, x Hermitian times a times x is a real number for all x. Okay, so in the dimension wise, so a is n by n. This is n by 1, so this is n by 1, and this n by 1 column vector has been multiplied by 1 by n row vector. So therefore, this is just 1 by 1. So which is just a real number, right? And which is just a single complex number. And we are claiming that this complex number is actually a real number. Why? So how do you prove that any complex number is a real number? So to prove that, there is very typical trick to prove any complex number is a real number. So that is, you take the conjugate of that complex number. And if the complex number is unchanged under the complex conjugate, then that is going to be the evidence that number is the real number, right? So I'm going to apply exactly the same trick over here. So yeah, so as I explained here before, this is a 1 by 1 matrix, right? And I am taking the complex conjugate of this 1 by 1 matrix. But for 1 by 1 matrix, taking complex conjugate is precisely the same as taking the Hermitian, right? Because the transpose of 1 by 1 matrix does nothing. So instead of doing the complex conjugate, so I am trying to do the Hermitian of this 1 by 1 matrix. Yeah, sounds very silly. Okay, but that is that. So this Hermitian complex complex conjugate. So conjugate transpose. So taking the conjugate transpose, so the order is now reversed. So x Hermitian times here, a Hermitian here times x Hermitian and Hermitian over there. Okay, but taking two Hermitians is same as doing nothing. So this x Hermitian is going to be x, and also we are assuming that x is a Hermitian matrix. So AH is now going to be A, right? So we compare this end and that end. They're just two same numbers. So we now know that this number must be the real number. Okay. All right. And proposition number 2. If A is a Hermitian matrix, then every eigenvalue of that Hermitian matrix must be real number. This is also very useful fact, because a priori, if for any complex matrices, the eigenvalue also should be some complex number. But if A is Hermitian, then eigenvalue must be always a real number. Why? So proof is also not complicated. So AX is lambda times x. X is some non-zero vector. So x is an eigenvector and lambda is eigenvalue. And I am multiplying the Hermitian of H to the both sides of this equation from the left. So here and there. So this number is lambda times x Hermitian and x. But x Hermitian x is the complex inner product of itself. So it should be understood as the length of complex vector x squared. And because of the proposition number 1, we also know that this number must be real number, right? So solving this relation for lambda, so lambda is xhax divided by the length of x squared. And this denominator and numerator, they are both real numbers. Therefore, this resulting number lambda also must be a real number. Okay, so lambda is real. Great. All right. So what's next? The proposition number 3. A is Hermitian. Lambda 1 and lambda 2 with distinct eigenvalues of A corresponding to eigenvectors x1 and x2. So x1 is eigenvector of lambda 1 and x2 is eigenvector of lambda 2. And lambda 1 and lambda 2 are different. Then lambda 1 inner product with x1 inner product with x2 equals to 0. In other words, they are orthogonal vectors. Yeah, so this is very important. So like a couple of weeks ago, so I tried to explain that for any matrix, suppose that your matrix A has 2 distinct eigenvalues, lambda 1 and lambda 2. And for eigenvectors x1 and x2 of these eigenvalues, we have proved that those eigenvectors that are automatically linearly independent if those 2 eigenvectors belong to 2 distinct eigenvalues. That was our theory, right? And this proposition is even trying to say even more than that. They are x1 and x2, they are not only orthogonal to each other, so they are not only linearly dependent, but they are orthogonal vectors, right? If A is Hermitian, right? Right? Yeah. Yeah. So although this proposition number 3 sounds like a statement on the complex matrices, but we have a real version of the statement. So that is, if your real matrix A is symmetric, and then every eigenvectors x1 and x2 that belongs to 2 distinct eigenvalues, then they are orthogonal. x1 transpose x2 should be 0, right? Okay, so even though this sounds like the complex statement on the complex matrices, but this is we still have the real version of the same statement. Okay, all right. Yeah, okay. So proof. So A times x1 is lambda 1 times x1, and A times x2 is lambda 2 times x2. And I am trying to compute this lambda 1 x1 inner product of this guy with x2. But lambda 1 x1 can be replaced by A times x1. And since this is Hermitian, so x1 Hermitian A times x2. And well, here I am supposed to have Hermitian over here, but since we are assuming that A is Hermitian, so A Hermitian is the same as A. And again here, I am replacing A times x2 by lambda 2 times x2. So looking at this end and that end of this equation, lambda 1 times a complex inner product with x1 and x2 is lambda 2 times complex inner product of x1 and x2. Okay. So solving this, so I have this equation, and this guy is equals to 0. But this factor can never be 0. Why? Because lambda 1 and lambda 2, they are assumed to be different. So the only possible choice option for us is this guy 0. So x1 and x2, they must be perpendicular to each other, orthogonal to each other. Great. Now we are getting close to the most important theorem of today's lecture. So I will just cut to the point. So there are some matrices that allows diagonalization, but there are also some matrices that does not allow diagonalization, right? Well, if your matrix A allows diagonalization, then your Jordan form of the matrix is the same, is actually the diagonalization of your matrix. But if your matrix A does not allow diagonalization, then your Jordan form of the matrix should be some complicated like combinations of Jordan blocks. So I don't know. But if your Hermitian is the conclusion of this section is if your matrix is Hermitian, then your matrix always allows a diagonalization. Isn't that amazing? Yeah. So this is what I'm trying to prove here. Okay. So yeah, so we have a long way to go. We need to prove that. We need to prove lemma 1 and some theorem from another, complex analysis, some multivariable calculus, and lemma 2. Wow. And another theorem. Yeah, so there's a long way to go, but let me try to be truly honest. You don't actually need to know all these theorems. All you need to know is just try to understand the final statement. And if you know how to take advantage of the theorem, then you're good. Okay. I'm introducing the proof of theorem in order to obtain the mathematical completeness of this course. But okay, that's that. So if you somehow lose your track, so if you somehow lost during the proof, that's okay. Don't be discouraged. So lemma number 1. Let U be an invariant subspace of A. Oh, hold on. What is an invariant subspace? So for every vector U in this vector space, suppose that AU is also a member of U. So if your vector space subspace U satisfying this, then we say that it's an invariant subspace. So symbolically, so AU is the image of the vector space subspace U belongs to U. If this condition is true, then we say U is an invariant subspace. Suppose that, so U is an invariant subspace, then do you remember the orthogonal complement? Is orthogonal complement also must be the invariant of the vectors, invariant subspace of A. So that is the result. That is the conclusion. Okay, so why is that? Well, I have chosen some vector, arbitrary vector from the orthogonal complement of the invariant subspace U. Then for any vector U from here, then we are taking the inner product of U and AB. But somehow, for some reason, I take the Hermitian of that. Then, also, yeah. So we are assuming that A is a Hermitian matrix. So Hermitian of this guy should be that. Right, but A times U is a member of U. Why? Because we are assuming that U is an invariant subspace. And since B was chosen from the orthogonal complement of U, therefore this guy times a member of U should be 0, right? So this guy equals to 0. Therefore, and since some number, a 1-by-1 matrix Hermitian equals to 0, therefore this guy should be 0 as well, right? So that means inner product of U and AB equals to 0. So AB is and since my choice of U was also arbitrary, so AB is orthogonal to 0 for any arbitrary vector from U. Therefore, AB must be the member of the orthogonal complement of U. Okay. Okay. Great. To prove next lemma, we need the following theorem. I have also defined very weird-looking subset of n-dimensional complex space. So this is V is this is now subspace, but this is some subset of the n-dimensional complex space, which is a collection of unit n-dimensional complex vectors. So I say this is 2n-1 dimensional sphere. Hey, what is that? If you do not understand this, then why don't you just plug in n equals to 1 here? So if V is a 1-dimensional, complex vector, so if V is just a single complex number, then collection of all complex number whose magnitude equals to 1 is what? It's just a unit circle centered at the origin on the complex plane, right? And unit circle, so that is, in my book, so that is a 1-dimensional sphere. What if n equals 2 here? Then you are dealing with S is a collection of all vectors, two-dimensional vectors whose length equals to 1. Right? So it has two entries, and each of these entries has two real part and imaginary part. So essentially, C2 should be understood as R4, and you're interested and all such vectors is actually nothing but all the vectors in R4 whose length equals to 1. So this is very hard to visualize. I know. So you're working the 4-dimensional space, and this is 3-dimensional sphere. Yeah. So if you're interested in physics, then have you ever heard about the spinors? In spins, well, this is exactly this. This is exactly what appears in the spinors. So, well, I just forget it. So, sorry, forgive me. I just want to say that S is a closed and bounded set that it lies in the 2-dimensional Euclidean space. And for any continuous function f, f attains a maximum and minimum at some point in S. Okay, so this is the point. So just forget just forget about the 2n minus 1 dimension sphere. So what really matters here is S is an closed and bounded subset, and a continuous function f attains the maximum and minimum at some point. Okay. This lemma number 2 is maybe the trickiest one. So, but I will try my best to explain this. I have defined some continuous function from this n minus whatever this guy, and set S from R such that S of V is V Hermitian A times V. Because of theorem number 1, we know that this is always real, right? So this is a function from S to the real numbers. And if this small s attains a maximum at V0, then V0 is an eigenvector of A with eigenvalue as V0. So in this case, you are always guaranteed to find a eigenvector and eigenvalue for any invariant subspace. This is the key point. So, okay, why? Because, well, just choose any unit vector. Step number 1 is if V0 and U are orthogonal to each other, then the real part of this guy equals to 0. Okay, so how do I prove this? So I am introducing one parameterized vector. So I'm introducing a vector Vt, which is cosine t times V0, which is this vector, and plus sine t times this guy. Then I am computing the magnitude of length of this vector by taking this inner product. So I have some weird computation going on here. So this is not so some tedious computation is going on here. But because of this guy equals to 0, but this guy also equals to z, 0. So this guy, I can simply ignore these two terms. And we are assuming that V0 is a unit vector, right? And U is also a unit vector, and this guy 1. So this is just cosine square plus sine square, which is 1. So this is again a unit vector. So Vt is a unit vector for all t. So we now define, so these guys are also member of this space. So now I can compose this guy with the function s, so which I will call f of t. Then, well, by definition of s, so which is this, and some tedious computation here. And you have to notice that this guy complex conjugate is the same as the Hermitian of this, but which is this? So that means this is a complex conjugate of this number. Right. And so eventually, so this is a complex conjugate of that number. And if you add a complex number to its own complex conjugate, then you know that that is going to be 2 times of the real part of the original number. So therefore, this guy just carries over down there, and this guy carries over down here, and but this plus that is going to be, so this is sine sine 2t times the real part of this guy. Okay. All right, and since we have assumed that this function small s attains the maximum at v0, therefore this composed function f of t must attain the maximum when t equals to 0, right? Because if t equals to 0, then this is going to be v0. So taking the derivative of this function with respect to t and plugging in t equals to 0, then our probably gets 0, right? So we take a derivative, so this guy derivative is this, and this guy derivative is that, and this guy derivative is this. And if letting t equals to 0 here, then this guy is 0 and this guy is 0, right? And this guy is 1. So therefore, the real part of this number should be 0. Okay. Okay. And step number 2. So in step number 1, we proved that real part of this number equals to 0. And under the same hypothesis, now we are assuming that we are proving that the imaginary part of this number equals to 0. Why? Because u is a unit vector, so is I. So I times u is also a unit vector. Therefore, v0 taking inner product of v0 and this guy, which is also 0. So v0 and iu, they are perpendicular. Therefore, iu and v0, they are satisfying all these conditions given in step number 1. So their real part should be 0. So this v0 h times a times this guy, the real part of this guy is 0, which is this. But you know, the real part of this guy is actually the minus of the imaginary part of this one. So the imaginary part also must be 0. So combining step number 1 and step number 2, if u is a unit vector and if u is perpendicular to vector v0, then this guy should be 0 because real part and imaginary part, they are both 0. Okay. And step number 3. Now we are trying to prove the exactly same thing in this consequence, but this time dropping the condition that u is a unit vector. U is now just any vector which is orthogonal to v0, not necessarily unit vector. Okay, so v0 h times u equals to 0. Then, so this guy is, I normalize this vector. Then, since this guy is 0, and so this vector is also orthogonal to v0. Therefore, because of this consequence, so v0 times h times a times this unit vector also must be 0. But sending this guy to here, so I have this. So therefore, this guy also must be 0. Okay, right. The final part. v0 is an eigenvector of A with eigenvalue as v0. We consider the subspace. So this guy, this number, and this is one-dimensional subspace of Cn, and just choose any vector from the orthogonal complement of this space. So U. Then, because of our previous problem, step number 3, this number should be 0. And taking the complex, since A is a Hermitian, therefore AV0, everything Hermitian, U equals to 0. So that means U is also orthogonal to AV0, right? Okay. So since U has been chosen from arbitrarily from the orthogonal complement of this guy, so AV0 also must be the member of the span of this space, right? Okay, this is AC. Because this is one-dimensional space, therefore, I'm pretty sure that there is some complex number, lambda, such that AB0 is lambda times V0. But this eigenvalue lambda is what? So SV0 is V0HA V0, but A times V0 turns out to be lambda times V0. So I'm replacing this guy by lambda 0. So eventually this is going to be this. And since we are assuming that V0 was obtained from the unit vector, so this is lambda. So this lambda is actually turns out to be the function value of S at vector V0. Great. Great. Finally, the spectral theorem. So yeah, as the name suggests, this theorem is one of the nicest theorems. So maybe one of the greatest theorem that you can ever find, can ever expect in the linear algebra course. This is spectral theorem, 환상적인 정리, right? Why? Okay, so let me try to read the theorem. So if A is a Hermitian matrix, then A allows always a diagonalization. A is always diagonalizable. Why? Okay, so instead before I try to prove this, so I'll just emphasize the importance of the theorem. If your matrix A is Hermitian, then you can that always allows a diagonalization. On top of that, I can do even more. So, and if A is a Hermitian matrix, then every eigenspaces of distinct eigenvalues, they are always orthogonal, right? Because two eigenvectors that belong to distinct eigenspaces, they are automatically orthogonal, right? Because of that, you can, and also for any given single eigenspace, you can find a orthogonal eigenvectors. Well, maybe you can try to apply the Gram-Schmidt process to a single eigenspace. Then you can find eigenspace, the basis of the eigenspace consisting of orthonormal eigenvectors. Combining all this, then you can say something like this. If your matrix A is a Hermitian matrix, then you can find eigenbasis of Cn, which is mutually also normal to each other. So you can find not only eigenbases, but you can find mutually orthogonal eigenbases. Isn't that amazing? This is not something that you can expect from any arbitrary matrices. This is only true for Hermitian matrix. This is true for Hermitian matrix. Okay, so let me try to prove that. By the way, so allowing A having a diagonalization is if and only if considering A as a linear transformation from Cn to Cn, as this space Cn has this very nice direct sum decomposition consisting of the eigenspaces. Why? Because allowing a diagonalization means you can find a basis consisting of eigenvectors, right? And having such a nice eigenvectors means you have such a nice direct sum decomposition of Cn. We prove by induction on the dimension of matrix A. Suppose that A is a 1-by-1 matrix, then there's actually nothing to prove. Everything is very clear. So we can move on. And for inductive case, suppose that the induction hypothesis is true for n. Now, for n plus 1 by n plus 1 Hermitian matrix A, we now assume that this function, and this function is continuous on this set n-2n-1 dimensional sphere. So S must attain some maximum at V0. And we now know that S of V0 is an eigenvalue, and there is a non-trivial eigenspace. So this eigenspace, at least contains this vector here. So this eigenspace is a non-trivial subspace of Cn plus 1, right? So 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 this eigenspace is clearly an invariant subspace of A. And we are taking the orthogonal complement of this guy. So this is again invariant subspace of A. Why? Because if this guy is an invariant subspace, then its orthogonal complement is also invariant subspace. So therefore, applying the induction hypothesis to this space, well, since this is the ambient space has dimension of n+1, but this guy has dimension less than n+1, right? And if dimension of this guy is less than n+1, so we can apply the induction hypothesis. So this guy allows these directors of decomposition, and therefore replacing this guy by this, so this Cn has this directors of decomposition. So A is diagonalizable. Okay. All right. So this is the end of the story.